Hello everyone, welcome to the OpenCL and SYCL conference of 2022. In this presentation, we will explore safety-critical SYCL or SYCL SC. My name is Ken Wenger. I'm the Senior Director of Research and Innovation at Core AVI. We provide safety-critical GPU acceleration platforms using open standards. As a company, we have a long history of collaboration with Kronos, contributing to safety-critical standards like OpenGL SC2, as well as being a main contributor to the Vulkan SC standard and chairing the Vulkan SC working group. On a personal note, my role involves researching functional safety and determinism in machine learning and general compute platforms. I lead the design team behind Core AVI's Safe AI platform, and together with Verena Beckham of CodePlay, I co-chair the SYCL SC Exploratory Forum at Kronos.
Hi, I'm Verena Beckham, and I'm the VP of Safety Engineering at CodePlay. At CodePlay, we're all about enabling heterogeneous computing using open standards. CodePlay has a long history with Kronos. We were involved in OpenCL very early on, and were then the main contributor to SYCL 1.2, developing the very first conformant implementation. We've also chaired the SYCL working group since the beginning. We started by supporting heterogeneous computing for computer games. Then we did the same for mobile phone applications. More recently, we are enabling heterogeneous compute on supercomputers. And now we want to unlock the same benefits for the safety-critical industries as well. Today we want to talk about the SYCL SC Exploratory Forum we created within Kronos with the goal of launching a working group to define the SYCL SC spec. We will start by giving you a bit of a background on the industry. We're going to discuss use cases for compute and machine learning, and we will try to identify existing tools and APIs that developers are using today in non-safety critical or prototyping environments. Then we will see what tools and APIs are available for safety critical platforms and identify gaps that must be filled. We will explain why we believe SYCL SC is the missing link in the safety critical stack and explore some of the changes that could be made to SYCL to make a safety-critical version of the API. At the end, we will show you how you can get involved yourself in getting this new SC standard off the ground. Let me give you a bit of motivating background first. It's actually pretty surprising what a large amount of software is already running in a car, and that goes for any kind of reasonably modern car, even at the low end of pricing. The engine is controlled by software, for example. So is the braking, the lights, and many other features that we don't even realize. But more recently, the software in the car has started to be a major selling point. When you think about extra comfort features, such as automatic windscreen wipers or automatic lights, these are almost entirely software features that enhance your driving experience. At the high end, you are starting to see advanced driver assistance or ADAS features as well, which includes things like adaptive cruise control, automatic emergency braking, self-parking, and many other features. So we are moving towards what's called the software-defined vehicle, where you choose what car to buy based on what software it has installed. And beyond that, car companies are already planning on how to achieve the holy grail, which is the entirely autonomous vehicle, which will drive you anywhere you want without you even having to pay attention. But this shift towards software means that the industry has to evolve. For one, autonomous driving and a lot of the ADAS features rely on artificial intelligence algorithms. These are complex, high-level algorithms that require a lot of compute power. Traditionally, the software in a car has been simple C or possibly C++ algorithms at best. Often it would be written in assembly, or more likely, automatically generated from models using modeling tools. To support AI algorithms, however, the codebases are becoming very large and complex. They need to make use of high-level frameworks and libraries, otherwise they will quickly become unmanageable. Up to now, software has generally been rewritten for every new hardware platform. However, if you've just invested a big chunk of money writing a complex AI algorithm that is central to the value of your car, you can't afford to just throw it away and start again from scratch. So portability is becoming much more important. Another trend has been what is called centralization. There used to be many small electronic control units, one for every feature. But now that software is becoming dominant, that doesn't scale anymore. So these individual ECUs are replaced by a few larger central processing units, which include a CPU and accelerators and might run one or more full operating systems and a hypervisor. So the simple embedded processors, which tend to be homogeneous and single core, are being replaced by heterogeneous systems with multiple cores and threads, which are shared by several processors simultaneously. And in the past, for every individual ECU, a different team would write the software, and everyone might choose different programming paradigms. Now that you have a shared processor, it's beneficial to have a shared programming platform as well. And we would argue then that a high-level, portable, open standard API like SYCL would address a lot of these needs of modern automotive software development, if only we can make it safe enough to use in a car. A lot of the software in a car is safety critical. That is, if something goes wrong, then people may be harmed. So safety really is the most important feature of the software. Safety in this context means three things. You need to ensure that you have removed most of the bugs. However, you can never be sure that you have removed all of the bugs, so in case you encounter a bug, you need to make sure that the vehicle remains safe anyway. This can be done by, for example, running a separate monitor thread that checks that the application is still running in the expected way. If it stops working unexpectedly or hangs, then the system needs to have a fallback, perhaps a backup application on a different piece of hardware. If all fails, the vehicle needs to go in what we call a safe state, for example, navigate to the side of the road and stop. And finally, you need to ensure that your application covers all of your use cases, so you've analyzed all of the operating conditions that you need to cover. As you expect, there are safety standards that safety-critical software typically needs to adhere to. For example, ISO 26262 covers the first 2 points, which we call functional safety. And ISO 21448 covers SOTIF, which is the safety of the intended functionality. ISO 26262 includes very concrete guidelines. Guidelines for writing and tracking your requirements, for designing your software, for writing your code, and for testing it. Luckily, a large subset of coding guidelines within ISO 26262 is covered by the MISRA standard. MISRA has developed C as well as C++ guidelines, and a new version of their C++ guidelines is currently in development, due to be released very soon, I'm told. Those new guidelines will cover modern C++ and will be less restrictive on things like memory allocation and pointers compared to the previous C++ guidelines. We have been focusing on automotive so far, but there are other safety-critical industries that also have similar requirements, though different safety standards to follow. These include avionics, where the DO178C standard ensures safety. Avionics historically tends to be more safety-minded than automotive and therefore more conservative in its adoption of new technology. Some applications, in spaceflight particularly, tend to be more mission-critical instead of safety-critical, but a lot of the methods overlap. Nuclear, rail, and medical are more examples of safety-critical industries.
Okay, so let's begin with an example. Suppose we have a car that uses different sensors to understand its environment. Each sensor, whether it's a camera, a radar system, or a proximity sensor, captures raw data that serves as input into a perception pipeline. An application may perform a series of pre-processing operations on the video frames captured by the camera before attempting to analyze the frame for object detection. These operations often involve classical computer vision operations like image filtering, edge detection, or optical flow analysis. Deep learning algorithms based on convolutional neural networks can also be used to detect and classify objects in a scene. Other sensors may require different pre-processing techniques. Signal processing libraries like fast Fourier transformation libraries are key elements of a robust data processing toolkit. Once the data from each sensor has been processed and analyzed, the information must be combined in some way. This is where the phrase sensor fusion comes in. The system must gather information from many different sensors and process them in a way that leads to a prediction that results in an action in the environment. Thanks to the open source community and GPU vendors, there's a large ecosystem of tools to enable fast prototyping of solutions. Tools like TensorFlow, OpenCV, PyTorch, the Python scientific libraries, as well as SYCL and OpenCL implementations are just a few of the tools and frameworks that developers can use today to accelerate their development. Here we have color-coded some use cases matching the tools and frameworks that developers are using today to prototype the decision-making and autonomy pipelines. In purple, we have TensorFlow, OpenCV, and PyTorch as examples of high-level frameworks facilitating accelerated image processing, computer vision, and deep learning functionality. In orange, we have SYCL and vendor-specific APIs similar to SYCL, which provide a C++ level of parallel programming APIs that can be accelerated through specialized processors. These general compute APIs, like SYCL, are used as the glue that can combine the result of sensor data analysis into a decision-making algorithm that's often proprietary and serves as the differentiator between different solution providers. In red, we have lower-level APIs like OpenCL and Vulkan, which provide a direct interface to accelerator devices, but being at a lower level, closer to the metal, these APIs require some level of expertise and specialization from developers. For this reason, often developers rely on the higher-level APIs and frameworks for app development, and leave OpenCL and Vulkan for the backend to accelerate the execution of the higher-level APIs. As you can see, to implement a robust automation pipeline requires different tools and APIs. The higher-level APIs lower the barrier to entry for using complex algorithms, while the lower-level APIs can accelerate the higher-level ones on specialized processors. Unfortunately, progress in this realm may lead to a false sense of accomplishment, as solutions developed on non-safety critical software stacks face the insurmountable task of certifying the systems once implemented. The problem with the ecosystem discussed in the previous slides is that they're written using non-safety critical APIs. So while they're good for fast prototyping of solutions, certifying those solutions to high levels of criticality, both for the automotive ISO 26262 or avionics DO-178C standards, is not possible. The advantage of safety critical APIs is that they ensure that algorithms execute deterministically. This is important to ensure that mission-critical applications can run when required and as scheduled by the real-time operating system. When we look at the current landscape of what is available in the realm of SC APIs and tools, we see that for image processing and deep learning, we can rely on Khronos OpenVX 1.3 specification, which contains a safety-critical profile. To accelerate the frameworks and tools on the backend, we can rely on Khronos' Vulkan SC API, which provides safety-critical graphics and compute pipelines. But many of the tools that make up the machine learning and AI ecosystem today are written on top of APIs which are not safety-critical, including SYCL. We are missing a high-level parallel programming API that can combine the results of deep learning or signal processing tasks and generate task-specific predictions. SYCLsc can be used to bridge this gap. And furthermore, since many of the already popular frameworks, like TensorFlow, run through SYCL, SYCLsc can be used to bring many of the tools from the non-SC realm into the safety-critical domain. So why SYCLsc? Because most developers are already familiar with C++. Most frameworks and tools that developers are using today are written in C++ and are already accelerated through SYCL. So porting to SYCLsc should be possible. Khronos has a long track record of successfully producing SC APIs from existing APIs, for example, OpenGL-SC, Vulkan-SC, and OpenVX. SYCLsc is the next logical step to follow from SYCL. SYCLsc provides the missing link in today's safety-critical API stack. Vulkan-SC at the execution layer, OpenVX for vision and deep learning, and SYCLsc for everything in between. In this slide, we can see an example of how SYCLsc fits in the Khronos ecosystem. On the top, we can see that neural network models can be trained in the cloud using a variety of platforms. Some of these platforms, like TensorFlow, PyTorch, or Caffe, we have already discussed. Once the models are trained, they can be exported from the cloud and converted to the Khronos NNEF format. NNEF stands for Neural Network Exchange Format, and it is defined by Khronos to provide a standard neural network descriptor format for transferring trained models between different frameworks. Once the model is trained and it is converted to NNEF, it can be imported by an application and executed through the OpenVX API. The result of the OpenVX execution can be further processed by the application through SYCL as part of a robust decision-making algorithm. On the back end, we rely on Vulkan SE to accelerate the high-level APIs. This shows that a full safety-critical stack targeting different levels of abstraction is possible once we have SYCL SE. Next, I'd like to share some of the considerations and discussions that we're currently having for SYCL SE. First, the development process of SYCL SE will monitor future updates to the Vulkan SE specification. The goal is to maintain both specifications aligned so that future implementations of SYCL SE could be done on top of Vulkan SE. Next, we want to define what we mean by safety critical when we're talking about SYCL SE. The definition of safety critical in SYCL will be similar to that of Vulkan SE. We mean enabling deterministic execution of software in time and space. This means enabling the deterministic management of memory resources. There are ways that we can do this, for example, by disallowing dynamic memory allocations. A lot of this work still has to be defined. However, this is kind of the directions and the discussions that we're currently having. We also want to reduce the complexity of runtime code so that certification efforts can be minimized. We can reduce the complexity by removing redundant or development-specific APIs, as well as by moving shader compilation stage from online to offline. Other areas that we're focusing on are reducing undefined behavior in the API and documenting functions and usages of functions that can lead to undefined behavior. Finally, we also want to expand on the error handling APIs to provide a robust error handling and logging set of APIs for a safety critical application. Memory management is always a big topic in safety critical APIs. That is because the memory management APIs have a direct effect on the execution time of software and therefore affect determinism. Before we get into the details of this slide, let me just remind you that these are just discussion points and suggestions. We're still too early in the SYCL SE definition process to know what a working group will decide for the API. Indeed, we're still at the exploratory phase of SYCL SE. The reason memory allocations influence execution time is because a memory manager requires some time to find a block of memory for a given allocation. If dynamic allocations and freeing of memory is allowed, then you can imagine that the memory heap gets fragmented with some blocks that are in use and some blocks which are free. Moreover, the fragmentation of the heap, which may be shared between multiple processes, is a function of every single process that is running on the system at that time. This means that if we have an application, let's say application A, which performs a single allocation, the amount of time required to find a free block of memory for this allocation may be different each time we run application A. For this reason, safety-critical APIs like OpenGL SC1 and 2 and Vulkan SE have removed the ability to dynamically allocate and free resources at runtime. In fact, in Vulkan SE, the application tells the Vulkan SE implementation the amount of resources that the application will need for its lifetime during initialization. This way, the Vulkan implementation can ensure, or at least check, that the application will not run out of resources at runtime. These are just some of the thoughts on what we may do with SYCL SE. Handling of exceptions is often contentious, as they're not necessarily bad on their own, but they do present difficulties on safety-critical use cases. Some problems that exceptions present are that often they require dynamic memory allocations for state tracking. Their behavior depends on the compiler, which might make portability a problem in some embedded spaces. But the biggest complaint is usually that the amount of time required for unwinding through a number of functions is difficult to predict, and therefore it can lead to non-deterministic execution times. So if we remove exceptions from SYCL, what can we do in its place? And some possible solutions are replacing exceptions with more error codes, more fault logging in the implementation, which the application can access. For cases where an abort or a fatal error is detected, a callback out to the application may be implemented. Again, these are just ideas that are being discussed. Decisions on these topics will be made in the future. When it comes to safety-critical APIs, ideally, there would be no undefined behavior. Unfortunately, in complex environments, that's often impossible to achieve. Therefore, our goal is to minimize instances of undefined behavior in the API functions, and at least bound the conditions that could lead to undefined behavior. For example, in some instances, a failure may lead to the GPU crashing, but the entire system must not crash. In this case, the application can build contingencies for recovering from a GPU failure. The specification should also define valid usage for the API functions. This means that we can exactly predict the behavior of functions called under valid usage, and where it applies, we can document that breaking valid usage may lead to undefined behavior. Identifying the conditions that can lead to undefined behavior allows an application to build safeguards and makes for a safer system. In this slide, we're showing the Kronos exploratory forum process, which is a key part of defining a new specification. The SYCL specification is currently in the exploratory forum phase. Any company is welcome to join this phase at no cost or IP licensing obligations. There's a project NDA that must be signed to cover the exploratory group's discussions. The purpose of the exploratory forum is to explore if consensus can be built around the scope of work document to define the new API. Once the scope of work document is created, a Kronos working group can be created to begin the work of writing a new specification. Thank you for watching this presentation. I hope you've enjoyed it. Please join us at the SYCL Exploratory Forum for more discussion on SYCL. If you have any ideas or suggestions on how we can get from SYCL to safety-critical SYCL, we want to hear from you. Thank you.